Thank you very much. Thank you very much for inviting me to this great conference, to this great place. So my talk is about periods, power series, and integrated algebraic numbers. Here, periods, these are period numbers, not period functions. And I'm very happy to Tom Scanlon for this very nice tutorial, because this will be also very helpful for the talk, what is following. We start with the motivation. So period numbers play a fundamental role in transcendental number theory and arithmetic geometry. Well, I don't have to tell you about that. For example, they arise in pairing, singular homology, and algebraic de Rham homology. You have here sigma is a cycle, omega is an algebraic differential form. You integrate it and you obtain a period. A period can be formulated in a more elementary way, not at this high level. Here I give the definition of Concivis and Sage. What is a period? A period is a complex number whose real and imaginary parts are values of absolutely convergent integrals of rational functions with rational coefficients over domains in R to the n, given by polynomial inequalities with rational coefficients. So in other words, I integrate a function, semi-algebraic over Q, over a domain, semi-algebraic over Q. In the following, we consider periods that are real. This is no problem, because we can always separate real and imaginary part. And then such a real period is given by integral of a semi-algebraic function over Q on all of R to the n, which is absolute integral. So this is not weaker. One might think, where is here the domain? Well, we can always move the domain to the function by multiplying with the characteristic function. Okay. Here are examples for periods. For example, pi. Pi is a period because it's just the volume of the unit disk in the plane. For example, the logarithm of 2, logarithm of natural numbers, given by this integral of a semi-algebraic function defined over Q. Or, more complicated, theta function at natural numbers. Here is a description of theta 3 in terms of an integral. But here you see any dimension and integration any dimension, and this makes it very hard to compute such periods. And so it's not much is known about periods, so it's not known whether the Euler number E or the Euler constant gamma are periods. So what is the Euler constant? You have the logarithm, which is the antiderivative of 1 over x, and you compare it with the step function. And this limit exists as n tends to infinity, and this is the Euler constant.
Even more depressing, we don't know if 1 over pi is a period.
Yes. Yes. So periods are defined by interaction of algebraic geometry, so semi-algebraic over Q, and analysis, whereas analysis coming from integration. And integration is not a first order compared to differentiation. And this makes it hard, really. So what are the goals of my talk? Describe periods in a more formalized way and define new countable number systems in an analytic geometric way. So coming from homonymity, capturing the important mathematical constants. What is the starting point? Well, in the following way, one get periods. I take a real power series, which is algebraic over the rational polynomial ring. So a power series, which is semi-algebraic over Q. That's the same. I take its formal antiderivative. We have a power series, we can take its formal antiderivative. Algebraic power series are convergent. Taking the formal antiderivative, we have the same domain of conversion. And now I evaluate such a power series at a rational point in this domain of conversion. Examples. We start with the logarithmic series. So this is log of 1 plus x. As radius of conversion 1, 1/2 is contained in the domain of convergence. And so log 1/2, this period, is given by logarithmic series, which is the antiderivative of 1 over 1 plus x at these rational points. And log of 2 is just the negative of log 1/2. Next example, I take the arcsine series. That's the sine, inverse function is the arcsine. Sorry, that's true, but why is arcsine? Well, the derivative of arcsine is 1 over 1 plus x squared. So we have an antiderivative of an algebraic power series. The radius of conversion is again 1. I evaluate this at p over 6. At 1/2. This gives p over 6. And again, I have such an antiderivative, formal antiderivative of an algebraic power series at a rational point. Okay.
So this way you can't get all periods this way, right?
In some sense, yes.
All periods,
This is my result.
but just one integration?
No.
You'll need to repeatedly integrate.
It's coming. So next, I want to introduce the setting that in this process, in this iterative process, we obtain all periods. So we follow this approach. So we start with the power series, which are algebraic over the rational polynomial ring, the same as the power series, which are semi-algebraic over Q. We call them simply algebraic power series. We close them under taking formal antiderivatives iterated and nearby algebraic and geometric operations. What do I mean? Main definition here. We consider the smallest class of rings of power series which contain the algebraic series and are closed under taking reciprocals, rational polynomial substitutions, rational translations, and formal antiderivatives. So these are these algebraic geometry operations. Well, they are, I think, they're not rather natural.
You allow poles?
Sorry?
You allow poles? What do you mean by reciprocal?
I will explain it. So reciprocals indeed is only defined for power series we do not manage at the origin. And then I take the 1 over. For example, the reciprocal of 1 over 1 minus x is of course the well-known geometric series. Then rational polynomial substitution. I have a power series in my process, and I plug in polynomials over Q vanishing at the origin. So we replace the coordinates by rational polynomials vanishing at the origin. For example, if in my geometric series I plug in x1 plus x2, I get this power series in two variables. Rational translation. Well, I have convergent power series. And I know if I have a point in the domain, I can develop my conversion series at this point again in a power series. And if I have a point in the domain of conversions with rational coefficients, then I'm allowed to develop my given power series I have obtained in a process at such a point.
Only when you have also rational coefficients, the other point.
All rational points. So here, for example, if you have the geometric series, you develop it around the point 1/2, you obtain this power series. And formal antiderivatives, as before, this is the formal antiderivative we know of power series, but note that we have general power series of arbitrary many variables, not only one variable, but arbitrary many variables, and then you're allowed to take formal antiderivative with respect to any. For example, the formal antiderivative of the geometric series is, of course, this.
Right, yeah. And in the definition, you said you have a class of rings, just because you have for every
n.
variable.
For every n, yeah.
But he has these rational substitutions that involve several variables, so they are connected to different.
Of course,
Right.
yeah. Of course. Okay. And we call the series obtained in this way the integrated algebraic power series. And we obtain the following results. So, contributing to your questions. Well, first, theorem A. Well, I had this class starting from the algebraic power series and then closing under these operations, geometric algebraic operations. Then, well, I consider all the coefficients appearing in my integrated algebraic power series. Then these coefficients, they form a countable real closed field. And we call this the field of integrated algebraic numbers. Now,
I'm not sure if I followed one of the axioms correctly. When you make a substitution like x plus 1/2,
yeah,
you do it only when you have rational coefficients around 1/2.
No,
no. I only, so the important thing is that this here has to be rational.
Okay, yeah, because you said with rational components.
Yeah, because in general, I have x1 plus a1, x2 plus a2,
Okay,
x3
so,
plus
okay, the
a3.
components and not the coefficients. Okay, that was what was.
Okay, yeah.
Yeah.
Okay. So, the coefficients, they form a real closed field, which I call the field of integrated algebraic numbers, because algebraic power series, the coefficients are the algebraic numbers. Now I have the integrated algebraic numbers, I call the coefficients integrated algebraic numbers. And now contributing to your question, a period is an integrated algebraic number. So in this way, I obtain all periods, but of course, much likely much more, because it's easy that 1 over p is an integrated algebraic number. Why I am allowed to take reciprocals, for example. So, what do we have? Everything is more or less encoded in power series. Starting algebraically, and then doing this finitely many algebraic geometric operations. And the analysis is somehow reduced to the evaluation of power series at rational points. So the integration is completely moved to a formal integration. Okay. So what about theorem A? The central observation is here the following: that this system of integrated algebraic power series has very nice properties. And what I call it's a convergent analysis system. So first, I explain what I understand by a system of convergent power series, a convergent system. And then I explain what I understand by a convergent analysis system. So what is a system of convergent power series? So for each n in n0, I have Sn consists of power series in n variables. And Sn should be a subring of the ring of real convergent power series, which I denote by the following. The next is more or less for convenience that my rings Sn are closed under permuting variables. That's not really a problem because, for example, algebraic power series have these properties and so on. So all the natural classes have these properties. And for notation reasons, makes life easier because I can always express with respect to the last variable. And S0, which I denote by K, small k, this is a subfield of R. And all the coefficients arising here should be from K. And of course, also the polynomial should be in there. Okay. And this K is called the coefficient field. So algebraic power series, they have the coefficient field algebraic numbers. Integrated algebraic power series, they have the coefficient field integrated algebraic numbers. And what is a conversion system? Well, I'm working in a setting not of formal power series, but of conversion power series. And so we have here the property of translation. If I have a function in my system and a point in the domain of convergence, which has coordinates in my coefficient field, then I can develop my power series around this point. Okay.
Then following finite sequence, you can get any germ of an decontinuation, right?
Yes. I really want to have, let's say, always the maximum. So I always want to consider the complete domain of convergence.
Yeah, but I mean, even if you have to go, or even if it's not the domain of convergence, you can start like following
Yes.
the sequence.
Yes.
And
Yeah.
entire Riemann surface of the project.
Something like this, but at least, but all of my power series are always, let's say, local. They are defined on this domain of conversion. Yep. So it's important here that I'm not working on some neighborhood of zero, but I really need on all of the domain. Okay, and what is a conversion analysis system? It's a conversion system, just have been defined before, such that the following holds. Well, again, we are allowed to take reciprocals of power series not vanishing at the origin. Then the next one is also easy. restriction, some of the coordinates we can replace by 0. No problem. Closed undertaking derivatives. So we have a power series, conversion power series. The derivative is again a formal conversion power series. We need here that the derivative is again in there. And now we need some complexification. So what do I mean by this? If I have a real power series, conversion real power series is of course also a conversion complex power series. So it does not only converge on a neighborhood of 0 in R to the n, but also in C to the n. So I can plug in complex variables. So I have now 2 to the n real variables, x and y. Now I separate again. These are now then real power series in 2n variables, and they should be also in my system.
You just walk to begin with on a complex sum, something of the complex numbers. Would you get something different or?
But first I'm in a setting of omnimality, so I want to start real. Yeah, but should be no problem. Just go add I to the field I have, then it should be the same now. And integration, I allow formal integration with respect to any variable. Note that we have permutation of the variables. So that's what I'm calling a conversion analysis system. And the following implications holds. One can show if I have a conversion analysis system, I obtain what's a so-called conversion Weierstrass system. What is a conversion Weierstrass system? So Tom also had this in his talk, these notions. So it's a conversion systems where I have Weierstrass division and preparation in my system. And then by all results of the Neff and Lipschitz, in a Weierstrass system, I have arbitrary substitution, I have compositional inverse of series, I have implicit series, and so on. So what is now a new feature compared to literature? So the Neff and Lipschitz, they consider formal systems on any field of characteristic 0. So far in the literature, systems of convergent power series on the reals. But now I'm working on subfields of the reals. So starting with the algebraic numbers and doing closure operations, I change my field. Examples. The system of algebraic power series is a convergent Weierstrass system with coefficient field A of real algebraic numbers. But it's not an analysis system because I do not have formal integration. But my system of integrated algebraic power series is a convergent analysis system with coefficient field by definition, which I called IA of integrated algebraic numbers. So here one has to do some work. Why? Let's go back. This is done by our setting. This is also no problem. Derivative, we don't have formulated in our definition of integrated algebraic power series. One has to prove this, that this holds. And one has to prove that the complexification holds. This is again by our setting. Okay.
In particular, it's also a Weierstrass system.
Yes. This is a Weierstrass system. But so we have in our analysis system is more. And there is a observation that you have a conversion Weierstrass system on a subfield of the reals, then this field is real closed. not too hard to show. Because we have by Dirac-Lipschitz these inbuilt functions. So if a polynomial which has a root in the reals, this root has already to be downstairs in the field. And this gives theorem A. Why? Our system is a conversion analysis system. Conversion analysis system is a conversion Weierstrass system. And this is gives theorem A. Okay. How about theorem B? Now omnimality comes into the game. Tom has defined or given in his tutorial the notion of a restricted analytic function. And I do now the same. So it is a restricted integrated algebraic function is the following. I take an integrated algebraic power series, conversion of the neighborhood of this closed unique cube, but only on this field. And outside, I extend it by 0. Okay. So this X only has components from this countable field. And let REA be the structure over the field IA by these restricted integrated algebraic functions. Now we want to understand this function. We introduce some languages. Natural, as in the case of AN, our AN structure. So L is the language of ordered rings. I extend it by symbols for every restricted integrated algebraic function. I add a symbol for the reciprocal, x is mapped to 1 over x. And I finally add symbols for every power function with rational exponent. Then following extending the work of Denef and Pannendries Mark and McIntyre, the paper which were mentioned by Tom, we get that the following holds for the structure, for this structure on the countable field of integrated algebraic numbers. First, the structure is omnimal. It has quantified animation in this language when I add reciprocal. And functions definable in this structure are piecewise given by terms in this biggest language. So the final function can piecewise also, well, the more or less compositions of polynomials, integrated, restricted integrated algebraic functions, and powers with rational exponents. Note that one can use, so in this proof, there at some points there are compactness arguments because they're working on the reals. We are working on a countable real closed field. We do not have the compactness arguments. That's why I need that I can do everything on the whole domain of convergence. So it's not enough to work on small neighborhoods around 0. I have to cover everything. Good. But now, remember, we are thinking of periods, there is integration needed. And now more comes into the game. So, integration in onmality, the fundamental result is by Lior-Rollard, Comte Lior-Rollard, about understanding parametric integration of functions definable in RAN. And this is based on Lior-Rollard preparation. namely the next, so following comp Lior-Rollin and also the extension by Dan Miller. Dan Miller extended this to, let's say, Weierstrass systems on the reals. We showed that this structure allows Lior-Rollin preparation. So it's different style of Weierstrass preparation. What is Lior-Rollin preparation? We have a function in variables x and a singular variable y, and piecewise I can prepare my function with respect to the y variables. How does it look like? So in Weierstrass preparation, we have something powers of y. Here you need a little bit coordinate substitution. So I take this translation, y minus theta x, where theta only depends on the first variables. Then I have here power with rational exponents. I have a prefactor depending only on x. And then here I have a unit. So what does unit mean? Unit means away from zero, away from the infinity. And the unit can be controlled. Namely, here again, functions of this form, finitely many, and I plug this in to a power series in our system, which is away from zero and infinity. So here, U is a restricted integrated algebraic power function or power series, not vanishing on this compact set. So therefore it's bounded from above and below on this compact set. So here now on the reals, this makes no difference. Then all this takes values in this unit interval, and the coefficients are rational, the exponents are rationals. So this is the Lior-Rollin preparation. Yep.
Yeah, of course, you mean the full Lior-Rollin preparation, right? There's an extra very important condition about the, this on the cell, the size of y minus theta x should be comparable to the size of.
Yes, of course. Yeah. I have the full, but for technical details.
Yeah.
So this is the qualitative version. Yeah. But I have the full. Yeah. And then, as stated, they used Lior-Rollin preparation to obtain results on integration. And we can follow this part. Now we can consider integrals in our structures with parameters. Now what is the setting? I have here a function in our structure, x parameters, y is now not a single variable anymore, arbitrary variety. So what to think of? X is a parameter, I integrate with respect to y. What do we have? The set of all parameters where this function is integrable with respect to y. This is again definable. Well, here one may think, why is it talking about integration on countable fields? So what is, well, but this has, of course, all a canonical lifting to the reals, interpretation of the reals, and there we have the integration. Okay. So the set of parameters is again here. And now on this set, I have this parameter integral.
Yep. Integrable means absolutely integrable.
Yes. There's a Lebesgue theory should be. Okay. So on this set in F, I have this parameter integral. And this can be described in a very nice way. Namely, there are functions definable in my structure. Here general ones, here positive ones, such that this parameter integral is given as a sum of products of my definable function and the logarithm of definable functions. And for this, I really need analysis system. So for Weierstrass system, at least I do not know how does it work. Okay, so to understand integration here, one only has to add the logarithm. So this was the nice result by Comte, Lyon, Rollard, and here we can achieve the same.
Surely this is not true for every Weierstrass system, right? It wouldn't be true for just the algebraic Weierstrass.
That's what I said. So it's true for conversion system. Oh yes, we were right, completely right. There we have a complex example. Okay. And now going back to periods. Well, in periods, we do not have a parameter. So a period, so far the result that a period well is a sum of products of integrated algebraic numbers and the logarithm of integrated algebraic numbers. But the field of integrated algebraic numbers is closed under the logarithm, which is also not hard to show, because the logarithmic series is in our setting. So this gives theorem D. And note that the previous theorem describes also families of periods. So let's say if I start here with something semi-algebraic over Q, then I have here a parameter family of periods, then they also have this nice description. Maybe this can be of some help somewhere. Okay. Next one, next step, what I call exponential integrated algebraic numbers. Well, we have seen that the field of integrated algebraic numbers is closed under the logarithm because we have the logarithmic series in there. But recall the integrated algebraic power series, they form a analysis system. Analysis system implies Weierstrass system. In Weierstrass system, we have compositional inverse. So we also have the exponential function. And this gives that the field of integrated algebraic numbers is, so this countable field is also closed under exponentiation.
It's kind of uniform.
So the exponential series is in my system. Yeah. And now, so I can expand the Ullmann structure by the exponential function, and which is again a structure on my countable Weierstrass field downstairs. And then following and extending again a paper of Van den Vries, Mark and McIntyre, this Engels paper Tom mentioned. The following holds for this structure on the field of integrated algebraic numbers. It is omnimal. It has quantify elimination in the language when I add exponential and lower. And again, functions definable in here are piecewise given patterns in here. Also quite nice that at least piecewise that the final functions are compositions of something I know. So it's built up of power series in my setting, exponential, logarithm. And now a definition. Exponential integrated algebraic number is the integral of a function of a integrable, absolutely integrable function definable in here. So a period was a definition of a function, semi-algebraic function over Q. That's the same as we have just shown before. It's the same that, so it's not, sorry, no, not the right thing to say, but here, that's my definition. An exponential integrated algebraic number is the integral of a function definable in here. And what is the result here? Well, this exponential integrated algebraic numbers, they give a countable ring, of course, containing the periods, but also containing the so-called exponential periods, and also the Euler constant gamma. What is an exponential period? It's a pity that Philip is not here anymore. So they have just written, I think, 2 papers about exponential periods. There are several notions of exponential periods. They have shown that they can use, for their purposes, they use a definition which works also in my setting. So what is an exponential period? This is given by integral of exponential of a function f, semi-algebraic over Q, but now this can also take values in the complex field. Times another semi-algebraic function over Q. And important, now I follow the definition of Annette Huber and Philip. In their definition, the imaginary part of f can be bounded. And that's why I'm in the omnimal business.
It should be absolutely integrable or something.
As always.
And still, even though it's absolutely integrable, they need the imaginary parts to be bounded.
They show that for their purposes, it's enough to work with this. Okay. So here, overview.
Sorry, how does gamma get into this?
Gamma has some integral, so they're even in Wikipedia. So there are some quite basic integral representations of gamma. So not too hard. Yep.
Okay.
Mhm.
Is there any familiar constant that isn't in this ring now of the exponential integrated algebraic numbers? Can you give any classical constant that isn't there?
I hope that's not.
Okay.
Okay. Well,
No, yeah, natural constant.
yes. So here's an overview. So I have omnimal structures, uncountable fields. And what do I get when I integrate absolutely integrable functions in this? The structures integration. So I start, what is the structure? Universe, where does the structure lives on? I apply integration. Which numbers do I get? Well, first structure, semi-algebraic sets and functions over Q. This is the same as the structure given by the restricted algebraic power functions. Here, this lives on the real algebraic numbers. When I integrate, by definition, I get the periods. Now I start with my integrated algebraic series, so with restricted integrated algebraic functions. This structure lives on this bigger countable really closed field.
Well, you think it's bigger. I know, that's
No,
definitely,
this
that's
is-
definitely big.
This is clear because pi
The
is in
end
here.
result, the end result for all we know could be the same.
If I integrate here, I stay in this. This was the previous theory.
Would it be generated by the figure? This figure?
Yeah.
How much bigger is it?
No, not generated. So I suppose it's really bigger. Because
We don't know, it's hard to prove that things are not.
yeah, of course,
very
but
big.
at least you see I have power series, I have to evaluate the iterational points and so on. So. Okay. Now, my third formula structure. So integrated algebraic series plus global exponential. Structure again on this countable field of integrated algebraic numbers. If I take integrals, by definition, what I call exponential integrated algebraic numbers. And now, about number systems, to show you the final picture. Well, the basics, the field of algebraic numbers. Then I've introduced this field of integrated algebraic numbers. I have this ring of periods, I denote by P. I have this ring of exponential periods in the sense of Harbaker and Huber. And I have introduced this ring of exponential integrated algebraic numbers. And here is the very colorful picture at the end. It's a little bit in the direction of Christmas or Hanukkah. So here we start. So this is the classical path. We start with the algebraic numbers. Then we have the periods. We know that pi is a period. 1 over pi, we don't know. E, we don't know, but I think people think that it's not. And the same for gamma. Now the exponential periods, E isn't there. But the question is gamma. And now this new path, let's say, P and E are integrated algebraic numbers. Gamma, I don't know. But now this integrated algebraic, exponential integrated algebraic numbers, we have P, E, and gamma. This is about constants, but I think the really interesting stuff is that these periods, families of periods, now is connected to nice Ummel structures. So really nice with all this quantifier animation, piecewise given by natural terms, and all on countable fields. Thank you very much.
In this picture, what is the relation between exponential periods and integrated algebraic numbers?
No. I don't know.
So do you know if the integrated algebraic numbers are the real closure of the periods or not?
I don't think so. But still these are really the hard problems. Yeah.
So you can show that the integrated exponential structure is closed under integration in the same way that the integrated algebraic one was closed under.
Not at all, because that's missing the result on integration of normality. We do not know how to deal with exponential function when integrating.
Do you get the Lyon Volan low exponential preparation? I know it's not good enough for integration.
Yes, but we can get this. This is no problem.
And my final question is, so let's say I give you a period.
Yeah.
So, I mean, it follows from what you said that it can be written as in a simple way using this integrated exponential stuff.
Yeah.
Sorry, integrated algebraic stuff.
Yeah.
So what would it take to actually give a bound, to show how you can write it? Is it only Lyon Roland? So suppose I told you that Lyon Roland you can do effectively and you know how many pieces, would it say that you can take any period and express it kind of effectively in this ring? Or are there some other sources of ineffectivity? And Lyon Roland has some compactness argument.
Oh, yes. So you mean to extract?
I mean, let's say I gave you a period of some
Yeah.
polynomial of
Yeah.
degree 10.
Okay.
So
Yeah.
do we know that when you can write it in this way with some expression of length?
So I give you the power series and so on. And so good point. Yeah.
Do you think that there's another? So I mean, where is the deep ineffectivity? Is it Lyon Roland or something else? Maybe it's a strange question for a modern theorist. You're just thinking about it.
Yeah, ineffectivity is again is in your talk. I think it's Liot-Roland preparation to find the cells. It is Liot-Roland preparation holds, and so on. Yeah, thank you.
For computing your period somehow, I mean, you integrate the function under the assumption that they are absolutely convergent.
Yeah.
I mean, is there a way to take into account when functions are not absolutely convergent? Just throw them away.
Well, first of all, in the one-dimensional case, there should be no problem also to deal with both cases. But in the higher dimensional cases, it's always quite unclear what does it mean not to be integrable, but not absolutely integrable. Because usually we're doing the back integral, and then integrable is the same as absolutely integrable.
We know the one group acts in the algebraic numbers, or maybe you use it really algebraic numbers.
Yes.
Complexification of it.
Yeah.
Does it act on any other of these sets?
Yeah, well, so we know that this is a real closed field. That's so.
So on the complication of it.
Yeah, well, you know, with a real closed field, you add square root of -1, you get the algebraically closed field.
So does the one of the rational, the absolute one of the rational number act on, it acts on A with R. But it's
Here, but it's not contained in cube R.
okay.
No. Because here we have transcendental numbers, for example, pi.
Can I ask you about this in the function field framework at all? Do you get anything new beyond? I mean, I assume you do, but beyond the exponential function and doing that.
I am not
No.
full less knowledge on this.
Let's then speak again.
So did I understand correctly that you have this canonical extension to R? I mean, from the, whenever you have a function in your language,
Yeah.
it has some canonical extension to R.
Yeah.
Are these functions always fucking? Because it seems that-
Yeah, I was thinking about this. So at least differential algebra or something like this.
I mean, because
Yeah.
basically you're only integrating.
Yeah,
right?
yeah,
And
yeah.
Integrating usually is fucking because you're just adding
Yes.
anything like
Yeah.
a prime is
Yeah.
equal to
Yeah.
something.
No. It should be somehow. Yeah.
So it's fucking because then you have some effective bounds.
Okay, I see.
We don't know it yet, but I think that Lyon Roland should be kind of effectivizable for this structure.
Yeah.
They would say that you can, given any period, you can really rewrite it in this form, which is
yeah.
surprising.
Okay.
It's not immediately you have some you have some complicated integral. How do you make it only into like antiderivative?
Yes, yes, at this
Not
point.
straightforward.
Yeah.
Okay, yeah.
Huh?
Very interesting.
Yeah, thank you.
Of course, all the questions that they asked you are probably super difficult. How to
Yes, that's-
show that anything is not in P is like impossible.
Yes, yeah, that's the point. That's the point. Yeah. Of course, well, there's a problem, but yes, let's say because I can formulate the same on the reals. And then, of course, talking about the definable functions so on without parameters. I get the same. But because the periods from this counter-theory I want to stress, so I want to work in a counter-theory closed field. But things work out. That's the motivation. Also, of course.
If you have general.
Yeah. Okay. Okay. Yeah. Questions.
Test code is small, and then, for example,
So I will take the question.
Because more or less you just take
I will get. That's what I.
Yeah. Because there should be some results that there are differential equations which cannot be expressed iteratively as antiderivatives.
But anyway. The image is not just take any whatever, take an ample one. Like
Die meisten anderen ja. Genau.
So the thing is that,
Ja, genau. Aber also was denn gesagt wäre,
Oh, yeah, so,
auf diesen Körper
can we do something like the
mit
following?
diesen Integrierten, mit dieser unrealen Struktur, da könnte man vielleicht dieses Couple-Mount durchführen. Technisch einfacher. Ja, also muss man nicht ständig diese Integrale nutzen.
Yeah.
ja, ja,
natürlich.
natürlich. Im Grunde ist, also ich glaube, dass deine Konstruktion oder eigentlich sehr ähnlich sagt dem, was die eigentlich Sachen wollten.
Genau.
Was aber, wo sie aber nicht, ist das nicht impliziert. Das sind so bestimmten technischen Schritt
I
halt
think
nicht
a good example to see.
Genau, weil in der wirklichen Sprache viel und nicht in dieser Sprache sind. Ich weiß, genau.
Ja, genau. Und die haben wir ganz kommentiert. Genau. Und das schon, natürlich ist das, also die Frage, ob man wenn man jetzt wirklich rechnet, dann sieht aber das ist ja die Frage, was
So, now.
das ist das, was mich jetzt ja,
Aber genau, well. Aber ich sollte mir das mal
Yeah.
How does a, so, has it need, legitimately begin to.
האמת זה מעניין.
generate.
אתה יודע, מעניין שהוא לא חושב לעשות תקף בהקשר הזה בעצמו. זה בדיוק מה שהוא עושה.
And so if you want something at the boundary, which sort of captures those parameterization.
So it's a you attach sort of. Don't you?
Exactly, no, exactly.
Maybe once.
בדיון כאילו בהתחלה, אומרים אין לו דעתים
How does this all really, what does so really mean in a hardstreet perspective?
לא יודע, נראה לי,
You have this sort of.
פר נושא, לא טוב בינתיים.
A level one hard structure can be generated to weight one sort of hard structure. And there's an understood process for how your hard structures can be generated to these next.
כן, זה נגיד, נראה לי אולי בין הדברים.
From that perspective, it's very simple into the one, some sort of magnification such that the boundary get exactly the right sort of generation.
You know exactly what you want to add in. So what is your issue?
Right. What is your issue? So the
I mean,
question-
if there's some kind of.
אני שמח.
Well, there's a much. Yeah, no, well, thank you very much, and thank you for the really, that's a nice.
לא יודע, יש...
Thank you.
לא,
Right, well, so you know what you want to add in set theoretically.
Yeah.
The problem was always giving it algebraic or even a complex structure.
שים גז על התוכנית.
Because the way you want to think about
אבל...
it, what's one way you have to think this stuff?
התחלתי לראות
Let's
קצת,
talk
עוד
about
כדי
it.
אני מדבר עם אנשים.
The collapse.
איזה?
Okay,
דארק, טובה.
it's the same as with the Griffiths conjecture. You know, why is it big gap?
התחלתי לראות מדבר גרמנית שקוראים לה המספידה.
I see, so it's similar.
It's a similar kind of. Say something to. I mean,
נקרא
it
דארק
would be-
פשוט. כן, נקרא בנטפליקס. זה בנטפליקס.
It's a little, yeah, I mean, the approaches are a bit different. I don't know how to do it the same way. If you give us education, only mapping or something, which is even educate the complex. Complex.
נהדר. כאילו, זה בסך הכל,
Here.
כאילו אני עושה בדואלינגו, כן?
Maybe this.
זה לא שאני מתקשש, כן? אני
But
מבין,
I'm saying it very
אני יודע
algebraic.
לקרוא, אני יודע לכתוב, כאילו, מבין את העקרונות. אבל אז כשלשמוע ולהבין, פשוט יכול להיות שצריך לפתח.
Then you get a natural language like
Again.
the Griffin. Okay, the inside is this thing I was saying.
וזה הם לא עושים שום דבר.
Automatic or something. There's a well-known way to extend to the boundary.
Oh,
And you know that its global sections
בקטע שלי
should collapse exactly all the stuff. Sort of like that's why all the- So now you're gonna do is show ten global sections. It has global sections. So that should be raised at the same. Like the Griffith bundle was what's called.
גם אם אני...
It's not ample. Ample means separate everything. But here to begin with, you add too much at the boundary.
רגע,
And so
די, באמת.
one enough sections separate everything you should. It's a very algebraic way of saying.
כמה היית אפשר בשלב הזה?
Yeah, it's iterations and all this stuff. We're not always making it true. Keeping in mind whether it's true or not. Tantalizing kind of thing to try. Find some sort of.
הוא עכשיו פרופסור בתל אביב?
It'd be great to have. Although like they were saying, you can't have it. You can't have it on D1G itself.
well, could have it on transverse direction.
האמת שלא מבין.
Well, no, so you can't have it on D1G. Direction. Or at least lots of.
רמת השרון זה חלק מצבר, הצבר
Change what you're looking for, and then maybe you can't have it.
Well, maybe.
You can't have a convectification such as every transverse variety has a limit.
Some nice sort of kind of size. But maybe it means one family at a time, something kind of. Something. It's a interesting kind of world. It's a great.
No, because I'm looking about the.
Yeah. It's an interesting world because they haven't.
Yeah, that's really fantastic. Amazing.
Yeah, great fun.
I'm really thinking about what's on.
I've never seen Dallas actually structured on. Actually, that's actually.
I mean,
The only thing you can find the bigger O-sharp structure. You know what this bigger one is? No, but that's obviously good trade. Yeah. Yeah, I mean, instead it's a worker, it's already a worker on it. Perfectly satisfying. This thing's a function, okay, other than you don't move it on now, you're a job. Here.
Indeed, absolutely. After that, you've got everything. But yeah.
I'm a little confused when you said you don't have cell decomposition, of course you do have cell decomposition. You omit it. But you mean you don't have like. Whatever, bounded parameters, so that's probably something
Sharp cell.
sharp. Where that means,
Well, it had a bound, there was a
you
bound.
just want to bound a number of components. Yeah, it's interesting.
Yeah, no, that's stuff. Yeah, it's really amazing. And the sharp derivatives, and then it's so natural. If you've got differential equations around, then your derivatives do the nice thing. So natural.
Yeah, it makes a lot of sense. Very pretty, very pretty. All the stuff comes down to some really basic ideas. I read at some point, for my Minerva lecture, for instance, I looked up Polanski's Binomials theory.
Yes.
A little bit. I read something.
Sometimes they're not the right incidents. There are no insurance that it's like. or-
He rambles a bit. He rambles a bit. But the ideas are so pretty. I mean,
Oh, yeah.
this idea of like. Ultimately, it comes down to literally what I was saying. Take a curve, a real curve. Count the number of zeros. If you have zeros, you must have sign changes.
Yes,
That's sort of what it's all built out of. It's
Yeah.
Built out of that observation.
it's unbelievable.
You know, I took a class with him. When I was. I think when he was an undergrad, I think it was still a high school student, just for like fun, I went to see that. He was talking about binomials. I kind of regret that if I think of it later, maybe I understood more, maybe not. But he explained the real and algebraic theory and like. You know, Tarski-Seidenberg
Wow.
gave this algorithm, the Descartes rule of sign, counting all this stuff. Very pretty, very pretty. I realized, by the way, something that we're studying. Here's a thing we can't handle, and I think the world can't. A little surprising. So like elementary functions, like, okay, if you have log, you're all good. But let's say you don't join log. Let's say you join the inverse function to something like 1/x² plus log x.
The inverse function.
Yeah, so let's say I want to say. So I have a relation, I have a y. An element y, when I join an x, there's a 1/x² plus log x is y.
All right.
Which you know, differentiate, you can see very clearly what that means. dy with the x. Okay, that's not elementary. Okay.
Right, yeah.
Oh, okay.
The
It's a-
integral.
No, not the integral, no, sorry, just that function. Like adjoining this x is not an elementary extension.
Relative to y.
Yeah.
Yeah.
Mhm.
Yeah, that's, I mean, I guess I hadn't kind of thought about it. It's not obvious that it would be, and it's, yeah, it's sort of
I think it is, so I think
totally
this,
tied up, but yeah,
I think Reach's algorithm can't handle things like this.
right, because it's not an elementary function.
You can join one, of course, you're okay, but then you can switch perspective. You know, pretend you were starting with y, with x all along. And then join y, and then you're fine.
Yes.
But if you do this a couple times, then that trick that trick no longer works.
Okay, so that's, yeah, it's a much bigger space of things around.
Yeah. That's already something that I was playing with. I don't know, I keep trying to algorithm work. I'm at least trying to make it work for regular.
Oh, that is it. It's always a good idea, just, you know, if you can't make it work, make it bigger.
Yeah.
You know,
I suppose that's right.
decide more. But
So,
I guess
yeah.
all the same problems may
Can't
come
prove a
back.
theorem from a stronger theorem.
Well, but you may have better ways of finding.
No, but this is our. This is an integral of a period, the integral of the orbit form. 1/x plus 1/x.
One over X, oh yeah.
Yeah, give it a deck, give it a log. So yeah, that's what I was looking at this, our framework naturally encompasses. all
Is
this.
that true? One over X squared plus one over X cubed.
No, I'm saying if you look at the function 1/x squared plus log. If you differentiate it. You get 1/x plus 1/x cubed. And dx, combined by the constant. So if you integrate that, you get this function, so you're allowed to get log plus any rational function. We're allowed to look at it. And somehow logarithmic poles are actually.
Chris, can you hear us?
Oh, that's Chris.
Hi, yeah, I can hear you. Can you hear me?
Okay. Yeah, great.
Great.
Yeah, I'll make you co-host so you can share your screen if you like.
Okay, yeah, I'll do that now.
How are you feeling, Chris?
Yeah, I'm not bad, thanks, Jacob. How are you doing?
Good, good. You can't see me. I'll make myself visible to you. Is this visible?
Oh, I could see you. Yeah, I can definitely see you now.
Okay.
Yeah, I'm feeling better.
Okay, that's great to hear.
Knocked me out for well,
You're seeing here.
best part of a week, really. But
Sure. Oh, there you go.
is that okay?
Yeah, we got your.
Yeah, it's perfect.
We got your notepad, looks great.
So what do you see, Chris? I mean,
Yeah.
you actually see the back of.
He's seeing
Back
that.
of our
Yeah,
decks,
he's
yeah.
seeing one, yeah.
Yeah, I can see. I'm sort of facing the lectern.
Okay, so whoever needs to talk to you will just come up like.
Yeah. Well, we're kind of here and turn around.
Yeah.
Okay, good.
You're all set?
Or we, oh, it's time to provide, yeah.
Chris, can you hear us?
Yeah, I can hear you, Gal.
So there's a microphone.
Am I okay? There's no echo or anything?
No, you're good.
There's no.
Okay, so last talk for the morning is by Chris Dodd from Reading. That was here.
Right, thank you very much. Thank you for the introduction. So apologies, I can't see you. So if if I seem a bit strange, I just apologize in advance. Thank you very much, obviously, to the organizers for inviting me. I'm extremely sorry not to be there. I was very much looking forward to it, but COVID got me in the end. So alas, I'm at home. Anyway, I want to try and explain this work that we did with Gal Bignamini. The idea is essentially to reprove a theorem from a while ago, what I sometimes call geometric silver pink, but to prove it with new techniques that allow you to give some kind of effective treatment of this statement. So let me start with a little bit of setup, not too much, hopefully. So I need to fix for my talk a Shimura datum. So just to remind you, what I mean there is that G is a reductive algebraic group over Q. And just to make things simple, X will just be a Hermitian symmetric domain. And of course, these are sort of come together. G is associated with X in a natural way. So just to give some examples in case this is not so familiar. So I think the two examples to bear in mind are Cartesian products of GL2. Sorry. And associated with that is the Cartesian power of the upper half plane, or the other sort of standard example is the symplectic group and the associated Siegel upper half space. Of course, there's lots of Shimura varieties, but if you're not familiar with them, these are the two that are easiest to get your hands on. So for the talk, I just want to make a technical assumption that's, I don't think, really necessary, but it just avoids, reduces the chance of making wrong statements. So I want to assume that the center of my group is real compact. So obviously that's not actually the case in the examples I gave, but you can work around that very easily. And then I need level structure or an arithmetic group, gamma. So that sits inside G of Q, but G of Q itself doesn't actually act on X. It has a finite index subgroup that acts on X, which I just denote with a plus. And this guy here is an arithmetic group. And again, just for technical reasons, I want to assume that it's neat or torsion-free or sufficiently small, just to avoid mistakes. And then the quotient of X by this gamma is what I call today a Shimura variety, and I want to fix this for the talk. Okay. So I want to talk about the Zilber-Pink conjecture, which concerns the special subvarieties of this S. So let me just remind you the definition of those, at least partly. So there's a natural notion of a Shimura subdatum, right? A subgroup and a corresponding sub-Hermitian symmetric space. And if I have one of those, then I call this space XH a pre-special subvariety of X. And its image under this uniformization map from X to S, those are the objects that I call special subvarieties. Or Shimura subvarieties, if you like. So, yeah, the Zilber-Pink conjecture is, as most people know, concerns how does an arbitrary subvariety intersect these special subvarieties. So let me formulate that next. So fix now for the whole talk V in S, an irreducible subvariety. All my subvarieties will be irreducible. Then I want to talk about what are called the atypical subvarieties of V. So a subvariety W in V is atypical if two things hold. So one, W should be a component of an intersection of V with a special subvariety. But moreover, the dimension of W should be larger than you might ordinarily expect. So that is, the dimension of W is greater than the dimension of V plus the dimension of Z minus the dimension of S. In the normal circumstances, this would be the expected dimension, and for atypical, this goes up. So Zilberpink says the following, as I'm sure you mostly know. V contains only finitely many maximal atypical subvarieties. Okay, of course, there might be infinitely many, but when you restrict to maximal ones, the expectation is that there's only finitely many. But of course, so this conjecture is, I think, fair to say, completely open. Just to give a sense of that, so Harry talked about products of modular curves, and you can ask this question in, say, y1 cubed. Right, that's a Chaumont variety, and you could look at a curve there, and you could intersect it with the curves you get by imposing two modular polynomials on the coordinates. And so the conjecture is that you get finitely many points as long as C was a generic curve, but that conjecture is still open. Best result due to Philip Habiger and Jonathan Peeler. So this is a wide open conjecture, but I want to talk about an aspect of it is that is essentially resolved, which is the geometric side of it. And to do that, I just want to recast this slightly. It's not necessary to do this, but it helps me. So I want to recast it in the language of optimal subvarieties. So let W be a subvariety of V. Then there's some objects you can attach to W. So first of all, there's a smallest special subvariety that contains W. Okay, that's because special subvarieties intersect in finite unions of special subvarieties. So this is a well-defined object. There's the number delta W, which is the codimension of W in its so-called special closure. That's sometimes called the defect of W. I think that was something first introduced by Pink. And then a notion introduced, I believe, by Habiger and Peeler is the idea that W is optimal if this defect is minimal among all the subvarieties of V that contain it. So another way to say that is if W is strictly contained in a Y in V, then that Y has a larger defect than the W. So for example, maximal special subvarieties of V are optimal. Those are the most important ones, I think. And just to relate to the atypical notion that we had before, so max atypical implies optimal, which implies atypical. Okay, anyway, but so you can rephrase Zilberpink in terms of this language in an unsurprising way. And the statement is that the set of optimal subvarieties of V is finite. Okay, so this is very hard to do. But what you can study is a related notion, that namely those of weakly optimal subvarieties, which somehow is a way of throwing away the arithmetic and just studying the geometric problem. So let me try to explain this briefly. So to do so, we need to introduce the notion of weakly special subvarieties. So again, let me take a Shimura subdatum. And then, so H is a priori just a reductive group. If you quotient by the center, you get a semi-simple group that's actually the honest direct product of its simple normal subgroups. So you can partition those into two groups and write this adjoint group as a product. Maybe you have one of these groups trivial. You don't want to, you genuinely want a looser notion, but this gives you a decomposition of the corresponding Hermitian symmetric domain. And then I introduce the notation XH little x2 for this fiber, which is x1 times the point x2 in the second factor. And it's the image of such a thing for any choice of the little x2 is what we call a weakly special subvariety. So we've moved from a countable family of subvarieties in the special subvarieties to now an uncountable family. But with these weakly specials, you can define the analogous notions to before. So if you have a subvariety V, then you can define weakly special closure, the smallest weakly special containing W, the weakly special defect, and the idea of being weakly optimal. So just in analogy. So the geometric Zilber-Pink conjecture is about how these are distributed. Now the name is apt because it's not completely obvious, but not deep, to show that an optimal subvariety is weakly optimal. Okay, this is due to a property coined by Haber-Gapila known as the defect condition. And what that says is that the difference between weakly special defect and defect can only go down as you increase as you go to larger and larger subvarieties. So to be precise, if W is in Y, then the defect of Y minus its weakly special defect is at most the defect of W minus its weakly special defect. Okay, so now geometric Zilber-Pink. So in this generality, this is the theorem proved by myself and Jimbo Ren in 2018. But this was subsequent to work on products of modular curves by Haber-Gapila. I hope you don't mind writing initials like that. And then subsequently proved by Gao for mixed Chamois varieties, and then much more recently, Baldi, Klingler, Umo proved the analogous statement for an arbitrary variation of pure Hodge structures. So what does it say? There exists a finite set sigma of pre-special subvarieties such that if W in V is weakly optimal, then its weakly special closure, which of course determines W. W has, if it's weakly optimal, it has to be in particular a component of the intersection of V with the weakly special closure of W, has to be of the form pi xh x2 for some xh in this finite collection. So the motif is that the weakly optimal subvarieties of V come from finitely many families. So the proof of this fact is quite straightforward once you have the big pieces of the puzzle. So the main one is the Ax-Shanwell conjecture, which was sort of proved about the same time, I think, by Mock, Peeler, and Zimmerman in this generality. And what that allows you to do is essentially to recast what it means to be weakly optimal, or at least a corollary of Ax-Shanwell allows you to do this. So W being weakly optimal turns out to be equivalent to its pre-image upstairs, or the irreducible components of this pre-image, being Zariski optimal. So that's the notion of optimality just based in the Zariski topology. But once you have that characterization, you can then describe this Zariski optimal locus. In a definable way. So in a no minimal structure. And then that's powerful because that unsurprisingly yields the sort of finiteness that you're looking for in the same theorem. So what I want to talk about today is essentially a refinement of this geometric version of the Zilberfink conjecture, proved with different methods, which I think are quite powerful and have appeared recently in other works in the subject. So let me introduce the machinery first. So the main player in all this is, for a Shimura variety, what's called the standard principal bundle. So this is an algebraic principal bundle that analytically arises by taking the product of X with the complex points of G and then quotienting by the diagonal action of gamma, which acts naturally on the two objects above. This is called the standard principal bundle. So this has an obvious morphism down to S, I'll call pi p. Fortunately, there's going to be a few pi's flying around, but it's not too bad. And it has another algebraic map, which I call beta, which goes to the compact dual of the Hermitian symmetric domain. And this map takes the class of X comma G to the Hodge filtration given by G minus 1 Fx, where Fx is the Hodge filtration naturally associated with the Hodge structure X. So of course, if these are new things to you, it's not so useful for me to go into technicalities. But what I think is poignant here is that we've replaced the original diagram, which is the covering of S by this symmetric space by a transcendental map. And we've replaced it with completely algebraic objects and two algebraic maps, one of which goes to a space very much like X. So rather than X covering S, there's kind of a sort of a universal guide P that relates the two in an algebraic way. And importantly for this talk, well, it's nothing to do with Chamois varieties, but this standard principal bundle has a canonical foliation on it. The leaves of which are of dimension equal to the dimension of X, and there's a unique leaf through each point P, and I denote that by curly LP. So this is the main tool. I need another sort of bookkeeping device, which will be a certain Chow variety. So first of all, to do that, I want to just fix a number. And this should be a bound on the degrees of the pre-special subvarieties of X. So those subvarieties come in finitely many G of R orbits, so it's trivial that there's a bound on their degrees, and it's not so important why, but I have to fix this number. And then I want to look at Chow variety, so to know omega, which is parameterizing irreducible subvarieties of X check that have, for varying K, codimension at most K and degree at most D to the K plus 1. And this is for all K. Of course, only finitely many K play a role because the thing is finite dimensional, but I have to do this just for technical reasons. So it's a Chow variety of certain irreducible subvarieties of bounded degree of X check. And then lastly, I want to make a remark about what happens if I bring a special subvariety into the picture. So suppose now I have an, sorry. I wanted a Shimura subdatum. And suppose the pre-special XH splits in some prescribed way, x1 times x2. Then choose the natural arithmetic group, the one you get by intersecting gamma with HQ lower plus. Then you can consider the standard principal bundle of that special subvariety. And I'm also going to be interested in a sort of Chow subvariety of omega, and I'm actually only interested in subvarieties of the form XH little x2. Okay, anyway, so I'm going to be interested in subsets of P times the omega. But with this additional data, I get a diagram. So first of all, I have a subvariety, which is the standard principal bundle associated with H times this omega H. That's an injection. These two objects project to the respective Chamois varieties. So just projecting onto the first factor, then applying pi p. So firstly to S and then to SH, i.e. XH mod gamma H. that's obviously has a natural map to S, finite map. And then lastly, I have another Chamorro variety in play, which I call S2. And that will be the X2. So remember, XH is split into a product of two things, modulo some arithmetic subgroup of H2. So I'll just take the image of gamma H into H2. Okay, I want to give these a name, so let me call this one pi H, and let me give this one the name phi H. So I'm going to be interested in, as I say, in subsets in P times gamma at the top right here, but I'm going to want to do a regular construction. So I'll take a subset here, I'm going to pull it back to here, and then send it down here. This will then, of course, give me a family, namely what I got here over its image down here. And I want to take the union of the Zariski closures of that family. So I'm going to invent notation for that. Okay, so for a subset pi, say, capital pi in P times gamma, I will let pi subscript h equal the union of these Zariski closures of, so now I have to do this complicated guy. So I start with pi, I take its pre-image under iota h, then I send it down by pi h, and then I take phi h restricted to that set. Okay, and the point is that if pi is locally closed, as it shall be, then it's easy to see that pi h is a constructible set. Okay, so lots of gibberish, but in the end, I can now formulate the refined statement of geometric Zilberpink. So this is the result with Bignumini, which sort of middle of last year, I think. So what it says is that for each D, which will be the weakly special defect of the weakly optimal subvarieties you're considering, you obtain a locally closed subset, pi d, of the space P times omega. And for each irreducible component of pi d, so I usually write that pi d circ, there's a pre-special subvariety and a prescribed splitting of that pre-special subvariety, such that, so on the one hand, if W in V is weakly optimal, and its weakly special defect is D, then there exists an irreducible component of pi d, and then of course the associated xh equal x1 times x2, such that W is the image in S of an irreducible component of a fiber of phi h restricted to this union of Zariski closures of fibers. On the other hand, if you start with an irreducible component of pi d and its associated pre-special, and W is an irreducible component of a fiber of phi h restricted to pi d circ h, then the image of W in S is weakly optimal of weakly special defect equal to D. Okay, so it's a bit of a mouthful, but essentially what happens is there's finitely many fibers that are derived from locally closed subsets of this guy here. The actual, which give you finitely many families, which sort of sit in this morphism here. And the irreducible components of those fibers are precisely the weakly optimal subvarieties of defect D. Okay, so just a few lines about the proof, because the proof is essentially the same as in the O-minimal setting. You just replace O-minimality with the complex geometry coming from the standard principal bundle. So you have a basic set, theta, which is just the set of pairs py in p times omega, such that p belongs to the pre-image of V in the standard principal bundle intersected with the beta inverse of Y. That's just the set that you need to make the following function make sense. So this is the function that does all the work. So this delta function goes from theta to non-negative integers, and it sends py to the dimension at p of the leaf through p intersected with this set above. So p minus 1v intersected beta minus 1 of y. That's a rather strange looking set, but this dimension is the same thing as, well, if I write p as x comma g, then this dimension is the same thing as the dimension at x as g times y intersected with the pre-image of b. And these are sort of precisely the kind of things you sort of look at in the O-minimal theory when you want to intersect things upstairs with totally geodesic subvarieties of 1gy. So anyway, pi d is defined using this delta function. Ax-Shamwell plays exactly the same role, with converting weakly optimal into sort of more algebraic things. And the proof then imitates the same proof from before, the Haber-Gapita proof and the proof with Jimbo. And as I say, the only difference is that O-minimality was replaced essentially by complex geometry, complex algebraic geometry. So that it covers what I would consider the refined version of the theorem, but somehow I promised a facting statement. So there's two ways I want to address that. So first of all, there's the question of how complex are the PIDs and the weakly optimal subvarieties that you obtain. Can you say something about their degrees and so on? So that's the first topic. So to do that, I have to introduce some coordinates. So let U and S be some Zariski open dense subset such that the standard principal bundle trivializes over U. And then denote by U omega P restricted to U times omega, so an open subset of P, which by the above is U times GC times omega, and then embed that into some projective space using Bailey-Burrell on the U, some linear group coordinates on G, and some projective coordinates on the Chow variety. And then I can define a complexity of my PIDs. So remember, pi d is locally closed, so it's equal to, say, y minus z. Y and z are Zariski closed. And then I'll say that the complexity of pi d in U omega is simply the sum, the degree of y intersect U omega plus the degree of z intersect U omega. And so the two theorems are that, well, first of all, the complexity of UD is bounded. So the complexity of pi d in U omega is at most polynomial in the Bailey-Burrell degree of V. So this is for some polynomial Fs, depending only on S. But that also then allows you to get at the individual weakly optimals, so in particular maximal weakly specials. So there exists another polynomial depending only on S, such that if W in V is weakly optimal, then the degree of W is bounded by a polynomial in the degree of V. So the proof of this latter fact, given theorem 1, is essentially standard arguments from the theory of varieties. And intersection theory. It's really the proof of theorem 1 that uses the let's say differential algebraic geometry. So I just want to talk quickly about the idea behind theorem 1. So suppose you have an affine subvariety of dimension d, and on it a non-singular n-dimensional foliation generated, say, by n commuting vector fields. So let me write that as psi 1. My side's gone a bit awry, but so these are commuting vector fields. And then for a subvariety of X, we define sigma BFK to be the set of points P and V, such that the dimension of the intersection of the leaf through P with V is at least K. And the primary input is that this is a Zariski closed set that we can bound the degree of and actually construct from equations for X and F and B equations for. So the theorem is that the degree of sigma is bounded by a polynomial PD in the degree of X, the degree of B, and the degree of psi. And this is an explicit polynomial. Oops. And equations for theta are actually computable if you have them for X and B and so on. So this is essentially a consequence in large part of a relatively old result due to Gabrielov and Hovansky. Which says, not in exactly the same language, but it says something like this. So suppose you have n regular functions on your X, and you have a point P on your X. Then if this collection of regular functions has, when restricted to the leaf through P, has an isolated zero at P, then the multiplicity of this zero is bounded polynomially in terms of the degree of the vector fields and the degree of the regular functions. And again, this polynomial is really, really explicit. So then once you have that, the idea is essentially that, well, to study these points, it suffices to just prove, to look at points after some reduction where this intersection has positive dimension. But by the Gabrielov-Khovansky bound, that's the same thing as saying that its multiplicity is somehow larger than some computable bound. So then you're testing for isolated zeros of large multiplicity, and some results, for example, of Bignamini and others, means that can be tested by just applying essentially derivatives of your original P's, which are all polynomials of bounded degree. And that almost immediately generates the proof of theorem 1, which was the complexity of the pi-d's. So the last question, which is presumably the most meaningful, is can you actually compute the pi-d explicitly? And so the answer to that question is essentially yes. But of course, the problem is if you want to do such a thing in the setting, let's say, as we had above, you'd need all sorts of stuff that's rather hard to get your hands on. So you'd need, for example, explicit equations. For the projective embedding of S. Again, you need some explicit description of the canonical foliation or the connection I've written here on some trivializing chart of the standard principal bundle. And then even given this, you then need some equations for the subvariety V in S, which even by itself is a highly non-trivial problem, because the setting that's of most interest to me would be the subvariety, the closed Torelli locus inside a G. And of course, giving equations for this is essentially not fully resolved, as far as I understand. So the idea is instead of working somewhat needlessly within a large Chamois variety, you use the functoriality of the construction, which permits you to work sort of intrinsically over V. So just rather than say anything general, let me speak about an example. So suppose you have, say, a smooth morphism of smooth varieties. And let's say to increase our chances of having actually a system of equations, let's say relative dimension 1. So then after just doing a few technical manipulations, which I'll describe as imposing level structure, you can obtain a map from V to some AG, some moduli of abelian varieties, just by sending V to the Jacobian of the fiber of this family of V. And the point is that by functoriality, if you're given explicit equations, for this family, then you can construct an explicit affine cover, say V alpha of V, and explicit equation for, right, let me give this map here a name, iota, for the pullback of this set pi d over each open subset of V for any d. So in particular, if you were given an explicit set of equations for the family of, say, all genus G curves, then you really would be able to compute, in principle, the locus of, say, positive dimensional weakly special subvarieties in the closed Torelli locus, and in particular those ones that intersect the open part for some fixed G. And I think I should probably stop there. Thanks.
No, any question?
Can you repeat in what generality this is Gabriela Khovansky? Can you hear me actually, Chris?
Yeah, I can hear you. Sorry, what did you say?
Sorry, this Gabriela Khovansky result you're using?
Yeah.
So in what generality is this kind of thing true? Like, do you need your P1 through Pn here?
Yeah.
You write regular functions. You just mean like holomorphic functions? Or do you need any sort of
I just meant,
right? Given the statement.
sorry, when I said regular, I just mean algebraic functions on the variety.
Okay. Is there a similar thing known for, just thinking about derivatives, for like vector fields that are regular, or for?
It's quite likely. I mean, I tried to cast this in somehow like the most basic language I could understand. Gal is surely, if he's still there,
He's there, he's right next to me.
he's surely the one.
Yeah, so what do you want exactly?
Well, it seems like this is one of the main like impetuses to the dependency in your proof.
Sure.
So we have these transcendental covering maps, and so you get these sort of vector fields that kind of aren't quite algebraic, but they're very close. You can manipulate them to get a bunch of different things. Can you say something? I don't know, maybe in your complexity language or something not very complicated, then you can bound the zero multiplicity.
I mean, the idea here is that everything is really algebraic. The foliation itself is algebraic. You have vector fields, and they are algebraic, right? And that's always true also for variations of point structures, right?
Sure, it's true.
If they were, say, not algebraic but definable, sharply minimal structures, I mean, the same thing would work. But I mean, the question is, what do you have in mind? I mean, because usually the data is algebraic, and then I mean, this works and it's a very general computation, just involving some Euler characteristics and topological things, super general.
Okay, so anything in your sharp framework would also get us. Okay.
Questions?
Okay, so let's thank the speaker again.
Yeah.
Okay, well, there's us.
Go ahead.
Yeah, you can ask.
Chris, can you still hear us?
Chris, we have one more question.
Yeah.
Okay. Yeah, so actually, I was wondering, and there's a thing that Jonathan and I did. This is Tom, by the way.
Hi, Tom.
Yeah, the thing that Jonathan and I did on effective Zilberpink using
Yeah.
differential equations, but we formulated it differently. You know, we used kind of moved the nonlinear equations. I'm wondering whether you thought about. I was trying to piece together how this matches or doesn't match with what we were talking about. Have you thought about it at all?
So, Tom, the embarrassing thing is, yeah, I remember your paper coming out about the same time, and I also really wanted to try and see where there was overlap, and I sort of failed because I think if I recall, your results were in large part in the sort of function field.
Yeah, it's kind of the function fields case, but it includes this, I think. But,
Right.
But we kind of black box the differential equation, which
Uh-huh.
makes, like explicit computations of the bounds harder. Not as good, I guess.
Yeah, I mean, the honest answer is like it's something that I should have done before. And understanding, yeah, your paper would be high up on my list, but I can't speak particularly, helpfully about the overlap. presumably there is some.
Maybe I can add a comment. So as I recall in your paper, but you correct me if I'm wrong, I think you got a bound for what Chris called maybe atypical locus.
Yeah.
And not for each family separately. Like we get the families of defect D for each D, and that was actually with our report somehow required a lot of extra work for some reason. So I mean, getting it to so that really every weekly optimal is a fiber of one of these families. I mean, if you have many weekly optimals, maybe their union is containing a bigger weekly optimal, and you get this. They might hide each other, and somehow a lot of work. I mean, basically, it's probably the same idea more or less. Right? I mean, a lot of this technical statement that Chris gave was exactly to be able to capture all of the weekly optimals separately.
Yeah, that definitely was sort of my recollection at the time, that stratifying by each D, and also within the Ds, the individual irreducible components, because it became apparent to Gal and I that, yeah, you could have some family of weekly optimals whose union may be encapsulated some other weekly optimals. So as I say, I can't speak to your paper, but our focus was on really trying to cut out every single, the most refined description as we could. But yeah, obviously, I owe your paper much more time.
And then yours was for general variations of code structure. Right?
Yeah.
And ours was only Shimura. Well, presumably some of it might extend, but I mean, we used some properties of Bailey-Burrell to get this second part of the theorem, so I'm not quite sure.
Well, thank you again.
Chris, yeah, thanks for coming again with your COVID and everything, and breathing it out with the dog. That was very nice.
Yeah, thanks so much, Gal. Thanks to everyone. Yeah, I hope you enjoy the rest of the day.
All right, so we are heading out to lunch.
Okay, great. See you later.
Yeah.
See you, Chris.
Thanks, Chris.
Everyone's looking every which way. Thank you, Chris.
No, yeah, you can see where you are. There we are. Thanks, Chris.
See you later.
See you.
Exactly. No,
So they turn it off then.